All right, there we go. Covering chapter 12.2. Our objective today to identify applications of solubility principles, relate them to polarity and intermolecular forces, to describe the factors that change the solubility of solids and gases, and to define saturated, unsaturated, and supersaturated solutions. So by the time we're done here today, if I give you a formula like CCl4, for instance, or the description of a particular compound, you'll be able to determine its polarity and the intermolecular forces that it has and tell whether or not it's soluble in water. Then you're going to be able to explain how temperature, pressure, and the structure of compounds, things like polarity versus nonpolar molecules, affect the solubility of solids and gases. And then you're going to be able to explain how the addition of a crystal can affect a saturated solution, how it affects an unsaturated solution, and how the addition of a crystal affects a supersaturated solution. We'll show you a little demonstration of that as well. So should enjoy that. All right, so let's look at the dissolving process. When we look at dissolving, we have to realize that dissolving only happens at the interface between the solvent and the solute. Whatever they're coming in contact, that's the process where dissolving is going to be taking place. So the idea behind dissolving is that you have the ions and or molecules being surrounded by the solvent. Okay, so little particles are going to be surrounded by other particles, the solvent particles, and that is basically what dissolving is. Okay, it's the surrounding of one particle by another. So if we had a big chunk of, let me change my color here. If we had a big cube of sugar, right? Big cube of sugar sitting in some water, and that cube of sugar is going to have a whole bunch of tiny little pieces on it, right? And those little tiny pieces are going to get attacked by water molecules coming in, and those water molecules are going to surround that little chunk of sugar, and they're going to pull it off, okay? Molecule by molecule, they're going to be pulling off little pieces, and then they're going to surround that little piece of sugar by or with themselves, right, with the water. So the solvent is going to surround the solute in the dissolving process, okay? So that's what dissolving is all about, surrounding the ions or molecules, depending upon what you're dealing with the solvent. So you can speed up this process with a few different methods. So let's talk about each of these methods and talk about how you might be able to speed them up. First method here is the method of powdering the solid or crushing the solid up into smaller and smaller particles. Okay, now if you are increasing the surface area by crushing it up, which is obviously what we're doing, then you're increasing the number of particles that can come into contact with the solute in a given amount of time, right? So some more solvent can get in contact with more solute when you have crushed it up into smaller and smaller pieces, all right? So you have a greater surface area. It's more finely divided. You're going to end up having a faster dissolving process. So you've increased the speed by using a powder instead of by using large crystals. Now, a great way to think about this is cotton candy. If you guys have ever had cotton candy, you take cotton candy, you stick it into your mouth, and it just like just dissolves. It like just vanishes in your mouth all of a sudden. Well, that's because that cotton candy was very, very finely processed sugar, that was real powdery sugar that has been strung up into tiny little threads. And so as soon as you put it in your mouth, because it has such high surface area, it just immediately dissolves. And that is a great example of why dissolving works by increasing the surface area. Even though it's not really a powder, it's a powder that's been kind of put into a tiny little thread. You can also increase the speed of dissolving by stirring. Okay, now what's happening there? Well, you're just causing more collisions, right? But if you're stirring that substance up, then you're getting more water, okay, that is now, remember, the water would have just taken some sugar and now it's surrounded the sugar, but now if it can get pulled away and now some new water can come in and then cause more collisions with the solute particles, then you're going to end up with more and more dissolving taking place. So agitation is going to increase that dispersion of the solute, and you're going to end up having dissolving taking place at a faster rate. And of course, then you can also heat the solution. All right, heating the solution is going to increase the speed of dissolving. Why? Again, higher kinetic energy, right, means more motion. And so if you have particles of water that are moving around faster, you've got more collisions, which means you're going to be able to get more opportunity for these solvent particles to strike the solute particles, okay? And it's going to allow for the separation because you have more energy. Energy is required for the separation of the solute particles from solute because it causes, needs a little energy to break those bonds. And the solvent particles from the solvent particles, it needs a little bit more energy for those to separate out. And so kinetic energy is going to increase the frequency of collisions and give greater separation and dispersion processes. So those are the three ways that you can increase the speed of dissolving process. And again, these are for solids. We are going to talk about gases a little bit later, but right now we're just talking about the solids. Now, solubility is the measure of how well one substance dissolves in another. Now, there are some general terms that we use when we talk about solubility, and then there's some specific terms that we use. So when we say solubility, we can just generally say, hey, solubility of sugar is, pretty high. And that is it's a good term to use, and it can tell us a little bit about what's happening. But if I want to get to the scientific aspect of this, and I want to be very specific, then I want to talk about the specific concentration of that dissolved substance in my solvent at a specified temperature and pressure. So I can look at the temperature, I can look at the pressure, and I can say how much, okay, can I maximally get into it, right? The maximum concentration that I could actually dissolve of my solute in my solvent at a particular temperature and pressure. And that is technically defined as solubility, okay? So I can use solubility in the general sense, but if I want to speak about solubility specifically, I might come up with a very specific term to refer to it, okay? Now, if I have gotten to my maximum concentration of dissolved substance, I am now in a saturated solution. A saturated solution is a solution that has the maximum amount of concentrated or maximum amount of solute dissolved in my solvent. So for example, I could say, for instance, the solubility of sodium acetate is 46.4 grams in 100 grams of water at 20 degrees Celsius in 1 atmosphere. What does that mean? Well, that means that if I have 100 grams of water, I'm going to be able to take 46.4 grams of sodium acetate and dissolve it in there completely. 20 degrees Celsius has got to be my temperature. 1 atmosphere has got to be my pressure. But my maximum amount that I could dissolve in there will be 46.4 grams at that particular temperature and pressure in 100 grams of water. Now, be very careful to pay attention to whether or not you're at 100 grams of water. Like, look at your graph, okay, because these are all going to be on a graph. And if you want to look at that graph, pay attention to how many grams of water are in that particular label for your graph. This is usually going to be on your y-axis, and make sure that you understand how much water it's being dissolved into, because if you don't pay attention to that, some questions can kind of throw you off. They might give you 200 grams instead of 100 grams, something like that. There was a question that I just received in the chat that asks about whether or not miscible solutions can ever be saturated. Well, at the point that you are still miscible, then you are either unsaturated or you've gotten to the point where you're saturated, but you cannot be, basically that's the limit, right? If it's miscible, it's mixable. And so those two are still considered either unsaturated or they might possibly be saturated. If you think about supersaturation, we're going to talk about that here in a little bit, then there are situations where they're still miscible. But if you tried to mix anything more into them, then they are definitely not going to mix. And if you're at the saturation point, you can't mix anything additional into them, but they could still be miscible as far as the substances that are already there. So that's a good question there. All right, so solution equilibrium. Now, in one of the worksheets that we were working on, you may have also seen this term, okay? And equilibrium, by definition, is kind of dynamic. But if you do see the term dynamic equilibrium, then we're basically talking about the same thing. Sorry, that was a funky looking L there. Solution equilibrium basically just is saying, if you get to the point where you have saturated a solution and then you put in, some extra crystals, all right? Now those crystals are sitting at the bottom of the beaker, right? So here's my beaker and I put in a crystal. I might be looking at a really big, beaker that has some water in it, and it might be just one tiny little crystal down here, right? It doesn't have to be like this big chunk that you're seeing in this illustration, but they're just zooming into the molecular level, right, to the atomic level to help you see what's happening here. And what's happening is that you have reached equilibrium, meaning that some of the particles are leaving and some of the particles are coming in. That means that some particles are being dissolved and some particles are being crystallized, right? So you've got dissolution, the dissolving process, and you've got crystallization, which is a process where the parts that are actually in the liquid are coming and they're joining back in with a solid. And so this is happening at an equal rate. When you are at solution equilibrium or dynamic equilibrium, then you are at a place where particles are leaving, okay, and particles are coming back. In fact, if you were to look at the shape of this particle, right, or maybe it's that tiny little particle that's down there, right, that shape might actually be changing slightly over time as some particles leave from one part of the solution and other particles come in from another part of the solution. So this could actually be, even though it's sitting there over time, it could actually be changing shape, and you'd see a dynamic change because some particles are coming in and some particles are leaving. So this is solution equilibrium, also known as dynamic equilibrium. And again, dynamic equilibrium is almost it's almost redundant because equilibrium means that there's things that are taking place, in both directions all the time. All right, so let's talk about saturated solution versus unsaturated versus supersaturated. Now, a saturated solution, we've already said, is the maximum amount of solute that can be dissolved, okay? And so at equilibrium, your solubility is reached, okay? So you've now hit equilibrium, same number of particles are going out as are coming in. If you actually had any extra crystal in there. So an additional crystal, if I added to a saturated solution, is just going to settle to the bottom. It's not going to dissolve, okay? So it's just basically going to be like a suspension at this point, right? If I have a solution that's saturated and I put one additional crystal in, it can't dissolve because the maximum amount has been dissolved. So that one additional crystal is going to fall to the bottom, and it's going to sit there and it's going to, reach its dynamic equilibrium, and it's going to have the material going out and coming in at the same rate, okay? So this is where you've reached your maximum amount of solubility, right? Now, what happens if I have an unsaturated solution? Well, that means I can still fit more in, all right? So I have less solute in that solution than it can hold. It can still hold more. So when I add an additional crystal, that additional crystal is going to slowly dissolve, right? It's going to disappear because I can still add more material in it because it's not saturated. Now, again, that's assuming that your size of your crystal is not bigger than the actual amount that can still dissolve. If it's a small crystal and you still have some room to dissolve, you're obviously going to see that crystal disappear over time, okay? So unsaturated solution, you add a crystal, you're going to see it slowly dissolve and disappear. And again, this stuff will definitely be on a test, so make sure you know what happens here. And then finally, we have our supersaturated solution. Now, in this case, you have more solute dissolved into the solvent than it can naturally hold at that particular given temperature. You're like, well, then how can it hold it? Well, here's the process. Let's say I have a beaker, and in that beaker, I've got, actually, I'm going to draw that somewhere else here. I'm going to draw that up on the top. Well, here's my beaker. Got a little more room up here. And in that beaker, I have dissolved as much as I can possibly get. Like I've got it, and it's saturated, right? That's as most I can dissolve. And I put some more of my substance in here, like let's say my little salt shaker or whatever, and I'm shaking some of that stuff in here. And as I do so, I get these tiny little crystals that are just going to sit at the bottom, right? They're going to settle at the bottom. Why? Because it was already saturated. In order to make a supersaturated solution, I'm going to have to do something to get those crystals to dissolve. And so I'm going to have to heat them. All right, so here I'm applying a little bit of heat. These are my flames. All right, so I'm applying some heat to this. Now, as I apply heat to this, then I am going to get these little crystals to now be able to be dissolved. Because remember, if I increase the temperature of a substance, trying to dissolve all those little crystals now. If I increase the temperature of the substance, I've increased the kinetic energy. And what that means is that I can actually get more solvent dissolved into my solute, okay? And now, okay, so we just talked about the process here. You add more, and then you heat it, and then you cool it. Now, if I can cool it slowly and gently, I can create a stable but unstable, okay? It's a stable solution. I've got some of it right here, and you can see it's a liquid. And I've created a stable solution that is staying a liquid, but it's really actually unstable because it's not going to take much to change this thing, okay? I've cooled it down. This is regular temperature now, but if I were to add an additional crystal, then what's going to happen is it's going to crystallize basically everything that's there. Now, it's kind of a wild concept. What we have happening here is there are a bunch of water molecules that are surrounding sodium acetate. This is sodium acetate trihydrate, okay? And so I have a solution of sodium acetate trihydrate, and the water is surrounding the outside of the crystals. When I add an additional crystal to this substance, it's going to allow for more crystals to attach to that original seed crystal, and it continues to attach in a branching out pattern. And what happens is the water that's currently in there, and there's plenty of water in there, that water now gets basically funneled into the inside structure of the crystal. And each of those crystal structures on the outside are now holding water on the inside. And so it goes from water being on the outside of the crystal to water being on the inside of the crystal. And all that has to happen is for me to open this container. All right. Now, why is that? Well, if you look, you'll see some crystallization on the very top layer of this little cap. And so as soon as I open this, then a tiny little crystal, we might not even be able to see it, is able to drop in there, and this whole thing is going to start to crystallize. Now, this can happen just with pressure changes. I've seen it, just a pressure change can cause this to immediately churn into a solid and to recrystallize. Okay, so I'm going to kind of keep it at a side angle there just so you can kind of see it. Should be kind of a fun way to see that. All right, so I'm going to open it. I'm going to turn it to the side. You're going to see it all kind of crystallize. And maybe I'll do it kind of on the side here. Okay, so here we go. I'm going to add a crystal inside by opening it. And you can see it's all changing from being a liquid into a solid. So now you can see that it's all turned into a solid instantaneously, just recrystallize. And so again, it's so cool, but the crystal went from being on the inside where it's surrounded by water to the outside, and now it surrounds the water. Kind of like trick play. All right, so it's so much fun. That's what happens when you add an extra little crystal into a supersaturated solution. You're going to see that whole substance crystallize. That's so much fun, isn't it? All right, so factors that affect solubility. Well, we've talked about polarity before, okay? And you've learned about, why oil and water don't mix, right? And we talk about polarity. Well, that's the structural factor that affects solubility. Is it a polar substance or is it a nonpolar substance? So we want to talk about the structure here. So here we have lithium chloride and water. Well, in lithium chloride, you have these ions, right? So there's a positive charged ion and there's a negative charged ion there, right? So you've got ions. And remember, ions are polar. And water is polar. And polar substances like to be with polar substances. They're attracted to each other. It's like two magnets, right? The positive and negative charges are like the north and south poles. They're attracted to each other. And so they're going to surround each other. And so polar substances are going to dissolve in polar substances. But if I introduce toluene, which is a nonpolar substance, meaning there are no external charges here that are strong enough to really be attracted to an external charge that's on water, then what happens is that water's like, hey, you got a positive charge, you got a negative charge, you want to hook up? And toluene's like, no, man, I got nothing for you. And so water can hook up with water, but it is not going to be hooking up with the toluene. The toluene is going to be completely fine, just hanging out with the rest of the toluenes. The nonpolar substances are going to be next to each other. They have an attraction to each other that they do not have to the water. And so that's our structure, right? So factors that are affecting our solubility is the structure, first of all. The like dissolves like. Nonpolar substances are going to dissolve nonpolar substances. Okay, so nonpolar solvents dissolve nonpolar solutes. That's about polarity. Okay, structure that affects solubility. The polarity, whether or not it's polar or nonpolar, is going to affect it. Okay, polar solvents are going to dissolve polar solutes, right? They're attracted to each other because they both have charges. And if you have something that is defined as miscible, basically the way that you can talk about that and refer to that is that it's mixable, okay, or dissolvable. Excuse me. So a dissolvable substance is a miscible substance. Alcohol and water are what I like to call commiscible, okay? They are completely able to dissolve in each other at any amount, okay? It doesn't matter how much water you have and how little alcohol you have, or how much alcohol you have and how little water you have, that they're still going to be able to distribute themselves, and because of their polar attractions, they're going to be able to distribute themselves equally, or they're infinitely soluble. So this is a miscible substance. Not all substances are completely miscible, right? You're going to have some mixing that'll take place until it's a saturation point. So with alcohol and water, you never hit a saturation point, okay? You never get saturated, all right? That's what happens when it's commiscible, all right? You're never going to get a saturation point. Immiscible substances are not mixable. These guys are not able to mix, and at least not able to mix and stay mixed, right? It's like I could take oil and water, I could shake them up, and I'll create a whole bunch of little bubbles. But those things are going to basically separate out based upon their polarity, right? They're not going to stay mixable. They're not going to stay mixed together. And so this is not mixable or not dissolvable. They don't dissolve in each other. That's immiscible. Now, I got a good question that just came in that was asking about, what happens with soap. And soap is basically something that we might consider a surfactant, something that will allow for two things that are normally immiscible to become miscible, okay? And these things that normally are immiscible that become miscible because of a third party, in this case a surfactant like soap, those things are considered to be emulsions, okay? So we would create this temporary emulsion of oil and water by putting soap in there, and that basically allows for the two to be connected together, because soap has this unique property of having a polar head and a non-polar tail. And so what happens is those two things come together. The polar head hangs out with the water, the non-polar tail hangs out with the oil, and so it basically is holding on to an oil and a water at the same time, and so they kind of all go together. And that's called an emulsion. That's one type of emulsion that you might have. And so the question kind of says, is the soap considered a solute and a solvent? Yeah, it kind of is. But we actually call that like a surfactant typically is kind of, we have another name for that. All right. So next thing I want to do is I want you guys to look at each of these different substances. And we have to try to determine whether these are polar or non-polar, okay? Now, if it's an ionic, remember that's the same thing as polar. And this is going to make us go back to previous chapters where we had to remember how to determine polarity based upon the shape. So for instance, if we look at CCl4, we have carbon surrounded by 4 chlorines. And if you remember back to when we studied shapes, that this is a 109.5 degree angle between each one. And the structure for this is AB4, central atom and 4 bonding atoms, which means this is tetrahedral. And because these are all chlorine and they're all the same, this is considered a nonpolar molecule. And so a nonpolar molecule like this is not going to dissolve in water, right? Because water is polar. So this substance is nonpolar and would not dissolve in water. Would water dissolve in water? Yeah, absolutely. All right, polar and polar, right? And it's kind of, one of those things that you have to think about, this question here, which is kind of a question that drives me crazy when people ask it, is water wet? That one drives me crazy. I've got a 7-part TikTok series, if you guys want to watch it, that describes this. But basically, yeah, water's wet. Why? Because water bonds with water. And the whole reason that anything gets wet is because water is bonding with it. And so water is absolutely wet. All right, but if you want to hear more about it, you can hear me rant for 7 1-minute TikTok increments, and you can hear all about it. HCl Okay, hydrogen and chlorine are not the same, and they're pulling in opposite directions, so this is definitely polar, so this is definitely going to dissolve in water. H2, well, these two are the same, so this is going to be nonpolar, so this is not going to dissolve well in water. NH3, this is the nitrogen. It's got the 3 hydrogens on it, if you remember, and then it's got an electron pair up there. Okay, I'll let you think about that one. I'm going to ask another question about that here in a second. I2, and that looks like it's pulling evenly, right? 2 same things, so that's got to be nonpolar, so that's probably not going to dissolve in water too well. And then you have NaCl. If you remember, Cl has a minus sign, Na has a positive sign, okay? And so in this case, you've got a polar substance, so yeah, definitely going to dissolve in water, okay? So I'm going to leave this NH3 over here for you. Remember, these 2 electrons are different than the 3 hydrogens, and that is going to affect its dissolvability, right? So let's look at this question. Which of the following will dissolve in water? Okay, so I want you to throw your response into the chat. You've got to choose which ones you think are going to dissolve in water out of those. And there's another question in the chat. Let me look at that really quickly. Yeah, that's a good question. Okay. Mr. H, I got one, but not the other. Mr. S, you got, how about Mr. HS? No. Mr. SA, yes. Miss LT got one. Mr. SP got one. Miss LH, you got one. Mr. RL, you got one. Mr. MO, you got none. Mr. BG, oh my goodness. Okay, yeah, the last 2 of your answers. Okay, yeah, right. So as I'm answering this question, one of the students has asked a question about the gases, for instance, like oxygen, which is a nonpolar molecule, and it still has a degree of dissolvability in water, right? So a gas is dissolving in water like oxygen, and you are getting oxygen in the water. Fish could not live without the oxygen in the water, right? So we know that the oxygen is definitely in the water, and yet it's a nonpolar substance dissolved into the polar water. So the question is, what's the deal, right? Are we just saying this is an exception or what? No, everything, okay, everything is slightly soluble in anything else, okay? So that's kind of the exception, that we talk about solubility, and everything is slightly soluble. And so something like oxygen and nitrogen and other types of gases, and then there are some solids that are very, 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 slightly soluble, like if you think about gold, like how much gold is going to dissolve in water, right? These values are all just below a certain threshold. Now, I cannot tell you what that threshold is, but that's basically where the hand waving is, is at. It's like if they're below this threshold of solubility of how much can actually fit into it, then we still consider it insoluble, even though we do have a small amount dissolved into it. So that's a great question. And that's kind of what you have to look for. You have to look for what that certain threshold is. Now, in our class, you're just looking for polar versus nonpolar. So if it's nonpolar, you're basically saying it's mostly insoluble, right? In water. And if it's polar, then you're going to say it's mostly soluble in water. So that's the threshold you're going to look for. But yeah, if you were to go beyond that, then you would say, well, there is a threshold, and let's talk about those values. But you don't have to know those values. So that's a great question. All right. So which ones will dissolve in water? Yeah, many of you guys have thrown out the correct answers. You guys have been going for it here. It's B and D. Now remember that these 2 electrons that were on the ammonia, that those don't pull the same as the hydrogens do, right? Because the hydrogens have positive charges on them, and these electrons don't have a positive charge pulling on them. And so that makes this whole molecule polar. And so that's going to dissolve in water. And then sodium hydroxide, if you remember the formula for that, you had sodium, positive charge, hydroxide is a negative charged ion. So this is definitely going to be polar. CH4 is basically going to have the same structure that CCl4 does. And so that's going to be a nonpolar molecule, just like it. And then oil. Oil is basically a structure of a bunch of carbons surrounded by a bunch of hydrogens. Okay. And so when you look at the overall polarity of oil, it has a whole bunch of nonpolar poles, because you've got not polar pole, it's not pulling if it's not polar, right? But you've got these hydrogens pulling equally on every side, and so it balances out that pole. And so this is going to be a nonpolar substance, and again, won't really dissolve in water. All right, good questions there. Let's move on. So structure affects the solubility. What about pressure? All right, well, higher pressure is going to increase the solubility of gases. So if we look at this first illustration up here at the top, we can see that we've got 1, 2, 3, 4 red arrows, and then we've got 1, 2, 3, 4 green arrows, meaning that we've reached equilibrium at this point, okay? Same number of particles of gases that are going in as are coming out of the solution. But if we then add some pressure, okay, so here we've added some pressure, we've taken that lid and we've now pushed it down, we've decreased the amount of space. You'll notice that at least for a while, we've got more of the reds pushing in than we have of the greens pulling out, right? And so we've got more particles being put in for a little while, so that you see at the end, when it reaches equilibrium again, that we've got more particles in container C in the liquid part, right, than we do in container A, okay? And so what you see here is that we've increased the solubility of the gases. Now, we reestablished equilibrium. We still have the same number of particles of the, the reds going in as the greens are coming out. So we reestablished equilibrium, but the number of particles is much greater over here in C. So we increase the solubility of the gases, okay? So Henry's law basically states this. Solubility of a gas in a liquid is directly proportional to the partial pressure of that gas on the surface of the liquid. So if I have a greater partial pressure, then I'm going to have a greater solubility. And if I have a smaller partial pressure, then I'm going to have a lower solubility. Okay, so we're going to take a second and you guys can watch this video. I'm going to show it to you guys. And I'm pause the recording a little bit. So if you you'd like to watch this later on, you can watch this video and you can see Henry's law. But I'm not going to show it on this video. You'll have to watch it. Okay, so we saw with Henry's law, we saw a little example how methyl red had it basically turned yellow as we increased the amount of space, and so that decreased the amount of carbon dioxide that was dissolved into the liquid, so its pH was able to increase because there was less carbonic acid. And as we allowed that space to decrease again, the carbon dioxide was able to redissolve into that liquid, creating more carbonic acid, and so the pH decreased and it became more acidic, got down to a pH of 4.4 or less. So again, remember that there's little effect on the solubility of liquids and solids. This is really only having to do mostly with gases. Finally, let's look at the temperature's effect on the solubility of gases, and then we'll talk about the solubility of solids as well. So the temperature increase is going to decrease the solubility of gases. Okay, now if I were looking at solids, we would be looking at lines that would be going in exactly the opposite direction. Okay, the lines for solids would go up in that positive slope direction, and the lines of gases are at a negative slope. Okay, again, what is happening here? Well, what's happening is that you've got increased amount of kinetic energy. The particles of the solvent are heating up, right? And so those particles of the solvent are basically knocking into the particles of the solute, those gas particles, and basically just shoving them right out, right? So shoving them right out of solution. The more energy you have there, the less they're going to be able to stay. They're going to be escaping out of solution. Now, this factor itself is actually one of the factors that helps to describe why it is that we have a greater amount of biomass in some parts of our ocean than other parts of our ocean. if you look at the places where the great amount of biomass is, you're going to find that the greater amounts of biomass are in the Arctic regions, where the temperatures are colder, because you can have more dissolved oxygen in those Arctic regions than you can in the equatorial regions. So although we have great biodiversity in the equatorial regions, we actually have a whole lot of biomass in those Arctic regions. Okay, so this is why, whales and things like that, they're actually, going to be spending a lot of time eating a ton of food while they're up in those Arctic regions where there's plenty of biomass available. And that's because you can have more oxygen in the colder water, and more of it's able to dissolve, and so you can support more life there. So yeah, decreased solubility with an increase in temperature for gases. And again, it's pretty much the opposite with the solids. So gases are more soluble in water when the pressure is higher and when the temperature is lower, okay? So solubility of gases has to increase with an increase in pressure, and it's going to decrease with an increase in temperature. And that is with gases. So let's look at temperature with solids. Now, solids have an interesting relationship, and you'll notice that we've got a couple of exceptions here, okay? You notice the exception here that we have of sodium sulfate and cerium sulfate, that those are actually decreasing in their solubility with an increase in temperature. But those are the exceptions. The rule states that the higher the temperature, the more the substance you're going to be able to dissolve. Okay, and that's why you have these positive slopes in most all of these. Okay, now why is it that we have exceptions? Well, it has to do with the interplay between entropy and enthalpy. Now we'll learn more about enthalpy and entropy later on, but the idea here is that enthalpy you can kind of think of as heat energy, right? That's kind of like a heat energy. And if you think about what does that extra heat do? Well, the extra heat is going to allow for particles to separate away from each other. Okay. And so, for instance, if I have sodium and chlorine, they are liking each other. So why do they go away from each other? Well, I'm going to have to put energy into that, right, to break them apart. And so there's some energy that has to go into separating the ions, but there's also energy that goes into the idea that sodium now could be surrounded by waters, right? You could have a whole bunch of waters around it, and that's going to be energy favorable for that to happen, right? And so part of this is, going to be giving you energy. Part of it's going to be taking energy. And entropy has to do with, the order of a system is generally the way we think about it. And you can kind of think about the order of a crystal, like that sugar cube, right? And you can kind of think about the order of the sugar cube versus having it, a whole bunch of tiny little pieces spread out. And what's going to happen there? Like, why does that happen? And what kind of energy changes are taking place there? And so basically, if you are looking at these exceptions over here, you're looking at the exceptions. Where are you? You're looking at the exceptions that are there based upon the combination of these factors. And so some of the order of the sodium sulfate and the cerium sulfate might actually be causing the differences in some of those. All right, so let's look at these and let's see if you can figure out how to read a graph with regard to these, okay? Which salt is most soluble at 10 degrees Celsius? Notice my solubility over here is 100 grams of water is the amount of solvent I have, okay? And I want to know how many grams of the solute I have in 100 grams of water. And then down here, I have my temperature, right, in degrees Celsius that we're measuring. Now, if we give you questions on a test, pay attention to the values that we're giving you, because sometimes I know, at least on the review sheet, I think there's one that actually changes one of those values on you, and you have to kind of do some math for it. So you've got to be really careful to pay attention to those values there. But let's start with the top one. Which salt is most soluble at 10 degrees Celsius? So we go to 10 degrees Celsius, and we want to see which one's most soluble, which means which one can we get the most stuff dissolved in? Well, if we look over here at the cesium chloride, we can see it's way up here at like 170 something, right? So we can say that the cesium chloride is going to be the one that's most soluble. Nice, good answer. So in at 10 degrees Celsius. And again, yeah, I love it if you guys are seeing these answers, you can throw them into the chat before I actually give you the answer. That's awesome. And then we go to the next one. What is the solubility of KCl at 80 degrees Celsius? So we go down to 80 degrees Celsius. So we got to be looking at this line somewhere, right? And then we got to find KCl. So we got to find the one that says KCl. That's this one here. So that's that green line we're looking at. And we want to know how much we can get in there. So we got to look at this little spot right there, right? And we come over. That little spot right there is intersecting somewhere over here. And so we'd probably want to guess somewhere around maybe the 52 range, right? Because it looks like it's a little bit above the actual intersection of the line. So maybe 51, 52, 53, somewhere in that zone, number of grams, we'd say like 53 grams of potassium chloride per 100 grams of water. Yeah, good job. Okay, so then we go to the next one. If 100 grams of lithium chloride, so we got to find our lithium chloride. Where's lithium chloride? Lithium chloride is, I can't even find my pen. There it is. It's so hard to find my little pen sometimes. My lithium chloride is right here, okay? And so that's the blue line. I say if 100 grams of lithium chloride are dissolved in 100 grams of water. Oh, okay, so I must be at the 100 gram line right here, right? And so I've got to follow that 100 gram line over. And it says that I'm at 90 degrees Celsius, so I got to find my 90 degrees Celsius part. And so that's the spot that I'm at right there, 90 degrees Celsius, 100 grams. What type of solution is formed? Well, remember that anything on the line is considered saturated. Below the line is unsaturated. And then anything above the line is supersaturated. So because it's below the line, then it's got to be unsaturated. Now, again, why is that? What's happening there? Well, remember that if I have 100 grams, I'm actually able to keep dissolving and dissolving and dissolving and adding and adding and adding until I get all the way up here to 120 grams. So I can still add about another 20 grams before I hit my saturation point. And then I'd have to heat it if I wanted to keep it and get even higher up in here. So I'd have to heat it and then cool it down afterwards. Good. All right. Good answers there. Now, as we wrap up, I want to talk about two more concepts here. And one of them is just to kind of go into a little bit more detail with regard to this whole dissolving process and the energy that's going back and forth. So we have this delta H SOLN, okay, this little symbol here, and that is the enthalpy of solution. In other words, it's how much energy is required or how much energy is released when I dissolve a particular substance. Now, some substances are going to be cold when I dissolve them. Some substances are going to be hot when I dissolve them. And so I want to look at what components are interacting for this overall enthalpy change. So the first interaction is when my solvent has got to separate from my solvent. Okay, so like if I want to separate water and water, this is going to require energy because water wants to be next to the water, right? And so this is a process when I separate my solvent and solvent that's going to require energy. Same thing here with my solute. Let's say I have sodium and chlorine, right? If I had the sodium chloride and I need to separate the sodium ions from the chlorine ions and different sodiums away from different other particles that are in that solution, this is going to require energy as well. So if I want to get my ions into solution, and I think I'll go ahead and do it this way, just so that there's no confusion, even though that has to happen too. Let's just say that we're talking about the ion parts. If I want to separate those ion components, that's going to require energy as well. However, if I want to now let my H2O, which now has a negative part of the oxygen being attracted to the positive part of a sodium, because those are attracted to each other, that's actually going to be energy favorable, right? That's going to give off energy. Excuse me. And so this is an energy favorable part. So we might have two parts that require energy, but one part that gives off energy because it's actually more energy favorable. It's getting to a lower potential energy state there. And so if that's the case, then I have to add up all three of these. I've got to add up all three of these components to figure out whether or not my overall delta H of my solution, my overall enthalpy of solution, is going to be positive or negative. Okay, so let's look at that example in a little bit more detail. Hang on one second. I think I just unplugged my tablet with my foot. All right. So let's look in a little bit more detail here. So if we look at this diagram, the idea here is that we're going to take, let's say this is sugar, and we're trying to dissolve it into some water, right? So the first part is I've got to take my little piece of my green piece of sugar and separate it from the big block of sugar, right? Take that little piece and pull it away from the cube. I'm dissolving it. Now this is, again, separating these two parts, and so it takes energy to do this, right? So here my enthalpy over here says, hey, it's going to take energy. I got to put energy into the system to make those things break apart. And then I've got to put energy into my system to make my water molecules separate out enough to get that little stuff to fit in. So it takes energy to break it apart, to break the water apart. So I had to break apart the solute, and I had to break apart the solvent. And now my final step says, hey, now the particles are all happy to be next to each other. They're coming in toward the water's coming in toward the sugar. And so that's an energy favorable part. And so now it's going to be releasing energy. Now, here's the thing. If this big step here is bigger than the two steps here and here, then this is going to be exothermic, right? Now, if this big step, number 3, was not that big, what if the big step was only that big and it would only go down this far? Well, that means that this would be endothermic. So substances, when you dissolve them, you mix them together, it gets cool. Well, that's going to happen when this last step is not as big as those first two steps. But if this last step is really big and it's bigger than those first two steps, then it's going to be exothermic and it's going to give off heat. So dissolving things can actually be a combination of these 3 different components, right? So keep in mind that whether or not something might get warm or whether it might get cold as you dissolve it has to do with 3 components all added together here. Okay. So 2 last terms, and then we're going to be done with today's lecture. The first term here is dissociation. And so remember that this is basically the part of dissolving where you're breaking things apart. Okay. And remember, it takes energy, right? It takes energy to break things apart. Okay. And so dissociation is endothermic because it's absorbing energy, right? It takes energy, so it's absorbing it out of the environment. So dissociation is a separating of the existing ions in an ionic compound, and this is going to be endothermic. Then the other part of the dissolving, and again, this is kind of separating it into the two parts instead of 3 parts. What we just talked about was the 2 parts, but this is just 2 terms here. So dissociation is that part where you're taking apart the ions, and then solvation is the part where you're allowing the water molecules, right, to surround the ion. So here's my sodium ion and here's my chlorine ion. The water molecules are now surrounding it. This is called solvation. Particularly, it's called hydration if it has to do with water, right? Solvation if it happens to be a different type of solvent. But if the solvent particles are surrounding the solute particles, then this is called solvation. And again, remember, this is exothermic. It's giving off heat. All right, so gives off heat. Right, it's exothermic. It's going to become more energy favorable. So that's why you can see the energy released over there. Okay. So that's covered everything we wanted to cover today. Let's review our objectives here and our criteria and see how we've done. Given a solute formula, so for instance, something like NH3, or a description, I can determine its polarity. NH3 is polar, right? We figured out its shape, its balance of things. Therefore, I can tell you whether it's soluble in water. Yes, NH3 is soluble in water because NH3 is polar and so is water. I can explain how temperature, pressure, and structure affect the solubility of solids and gases. Yeah, each individually, right? You need to know that temperature can increase the solubility of solids, but decrease the solubility of gases. Increased pressure can increase the solubility of gases, but doesn't really affect the solubility of solids. And then the structure, polarity, right? The polarity affects solubility of solids and gases. The polar gases, although there's not a lot of those, let's just talk about polar solids. Polar solids are going to be more soluble, right, in polar substances, and nonpolar solids would be not very soluble in polar substances, but they would be soluble in nonpolar substances. And then I can explain how the addition of a crystal affects saturated, unsaturated, and supersaturated solution. Absolutely, right? You put a crystal into a saturated solution, it's going to just settle to the bottom. If you put it in an unsaturated solution, it's going to dissolve and disappear. You put it in a supersaturated solution, it's going to cause the crystallization of the entire structure. All right, so we've learned a lot today. Hope you guys had a good time enjoying the solutions and all the intricacies of solutions. I just love the part about chemistry where you're like, I have never thought that much about things that dissolve into each other. But if you get into the actual chemistry of it, you're like, wow, that's really amazing to see how all of that stuff interplays to actually allow things to become dissolved. So I hope you enjoy the beauty of that part of the chemistry as well.